let's get started. Our second to last day, so I'm going to say good morning to you all. All right, let's get going. I'm going to continue with the review. Don't forget tomorrow, or actually later today, I'll be posting the final exam periodic table instructions how to upload it, which you've seen before, not the final exam. Tomorrow at about 8:30 or maybe 8:15, I'll send out the password for the final exam. You'll have until 9 o'clock Friday to upload your answers as a single PDF file. Please do that. If you have any troubles, let me know. Plan on, normally when I give it in a classroom setting, most students are done within an hour and 20 minutes. But take as much time as you want, because I'm not going to be standing there and saying, time's up, 2 hours now. And plus, one of the things I realized long ago, either you know it or you don't. If you don't know it and you have as much time, it's not going to help. Hopefully you all know it. Actually, I do know most of you know it because you've been doing good this semester. Thank you. Makes my heart feel real good. Yep, real good. It's beating more because I'm feeling really good now. But anyways, again, I'll send out the email with the password tomorrow. Now, number of you have uploaded to me via email your labs. I'll try and get them done today or tomorrow. So if you're missing labs in Blackboard and you haven't sent me those missing labs, be sure to do it as soon as possible, because otherwise you're going to lose a lot of points and that's going to hurt your grade. All right, let's get started. I finished test number 2 review. I'm going to do test number 3 review right now. And I'll call on my thumbs up people. Do you see test 3 review? Thank you. You guys got the fastest thumbs up this side of the Mississippi and the other side too. All right, let's go through this. Test number 3 review. Start talking about gases. And the first important thing is, one thing you can measure of a gas is its pressure. And when we talk about pressure, we can have the units millimeters of mercury, and I taught you how a barometer worked in the old ones, where that came from. And that equals 1 torr, which is shortened for Torricelli, great Italian chemist who did a lot of work, important work with gases. Now, another important definition for pressures is 760 millimeters of mercury equals 7. I got the same thing both. Hold on. Instant correction. Double correction. All right, 760 torr equals 760 millimeters of mercury equal 1 atmosphere. And if we go to if I can find it, hold on. I lost one of my practice problem sets. Hang in there. Oh, now I know why. It was a PDF file. Sorry about that. All right, since I was playing around, thumbs up, people. You see the gas practice problem? Good. All right, let's take a look at number 1. How many torr is 41.5 millimeters of mercury? You're trying to find torr. You're given this. You start here. You want to go to torr. Use your good buddy, your good friend, unit analysis, and therefore torr go on top, millimeters of mercury there. It's 1 to 1, as you just saw. Remember, these are exact numbers, therefore, same thing. Now, if I come down to number 3, how many atmospheres is 741 torr? 741 torr is what we have. We're trying to find atmospheres. We're trying to go to atmospheres. Atmospheres goes on top because I'm using my good buddy and your good buddy, unit analysis, and your good friend too. And torr go underneath. Where do I get these numbers? 1 atmosphere equals 760 torr equals 760 millimeters of mercury. And if you look in the important information for final exam, which I recommend you all do today, you'll see that's given to you. 1 and 760 are exact numbers because that's the definition. Therefore, this is 3 significant figures. My answer has 3 significant figures. If we go down to number 5, if I can get there, how many millimeters is 4.564 times 10 to the 3rd atmospheres? We're trying to find millimeters of mercury. We're given atmospheres. Here's the number we start with. We're trying to get to this millimeters of mercury. That goes on top. Underneath goes atmospheres. And where do we get these? 1 atmosphere equals 760 millimeters of mercury equals 760 torr. And these are exact numbers. Remember, when you multiply or divide, the number that has the smallest significant figures is the number of significant figures for your answer. Well, these are exact numbers. They don't play a role. This is 4 significant figures. This is answer 4 significant figures. Since Zoom is playing games with me, does everybody see the review? Thumbs up, people. Thank you. You'd have to write on your thumb, Dr. White's thumbs up, people. No, you don't have to. All right, let's move on. Now, I talked about gas laws, and gas laws are mathematical relationships between various measurements or parameters of gases. And these were developed because during the Industrial Revolution, when the steam engine and later the gas or gasoline or combustion engine were developed and used. And the first one I want to give you is Boyle's law. Boyle's law is P1 times V1 equals P2 times V2. P1 is the initial pressure, V1 is the initial volume. P2 is the final pressure, V2 is the final volume. You'll be given 3 of these and asked to find a 4th. And if we look at the practice problem, number 6, if a balloon has a pressure of 658 torr and a volume of 1.894 liters, what is the pressure of the balloon if the volume is increased to 5.133 liters? Well, let's look at what are we being asked to find. What's the final pressure after you make a change? What are you given? The initial pressure, P1, is this number, 658 torr. The initial volume is 1.894, V1. And you're changing the volume to this, which is your final volume, V2. Now, ideal gas law? Nope. You use Boyle's law. Thought I'd trick you there. No, I didn't. But P1 times V1 equals P2 times V2. That's important information. Years ago, I used to make students memorize this, and as I've told you a number of times, I've come to the realization I'm here to test chemistry, not your memory, and at least for formulas. And so I gave this to you. What do we need to do? We need to solve for P2. But we have V2 here. How do we get rid of it? Anything divided by itself is number one. So if I divide this side by V2, it's gone. Whatever I do to one side, I have to do to the other. Therefore, now I have P2 equals V1 times P1 divided by V2. I'll rewrite it. And since I took the time to figure out what is P1, V1, and V2, I can immediately put those in. Now, if we look at this, this is three significant figures. This is 4. This is 4. What's the lowest number? 3. And that's why you have three significant figures. Everybody see a plain white screen? Thank you. And Dr. White's going to share. Hang in there. All right, let's go through this. A piston has a pressure of 632 torr at 4.331 liters. What happens to the pressure if the volume is reduced to 0.251 liters? Have fun. Your turn. Oh, by the way, important information. I'll give you it over here because you may not be able to see it. I won't write out, but P1 initial pressure, V1 initial volume, P2 final pressure, V2 final volume. Go. I remember when you're done, if I were in a classroom, I'd tell the class, look up and smile. But since I don't have all your videos, you can also do thumbs up. And if you're done, give me a thumbs up. Okay, let me do this. Before I do this, time for a commercial from Dr. White. Don't forget, tonight I'll have my office hours, my Zoom office hours from 6 to 7. And if you need any last minute help, stop by. I'll be there. End of the commercial from Dr. White. Bet you didn't realize you had to put up my commercials. All right, everybody should see the problem. Thumbs up, people. You say thank you. All right, let's do it. What are we being asked to find? If you look over here, hold on, what happens to the pressure? So we're trying to find the pressure, but really this is P2. The initial pressure is this, P1 equals 632 torr. The initial volume, V1, equals 4.331 liters. And the final volume, which is V2, is 0.251 liters. Because if you look right here, all you have is pressure and volume. You know Boyle's law, P1 times V1 equals P2 times V2. We want to solve for what? The pressure. So we want it alone. How do we do that? How do we get rid of V2? Divide by that. Whatever we do to one side, we have to do to the other. And remember, anything divided by itself equals the number 1. Therefore, 1 times anything is that thing. So we now have need to get more room. P2 equal V1 times P1 times V1 times V2. I like to rewrite it, you don't. And now we'll put the values in, 632 torr, 4.331 liters, divided by V2 is 0.251 liters. That's why it helps to do this, because it saves you time when you're doing this. And now we'll go to Dr. White's favorite calculator, courtesy of Bill Gates. All right, let me ask the thumbs up people. Can you see my spreadsheet? No, you can't. Now can you see my spreadsheet? If you do the work, you get this number, or if it's in scientific notation, if you go back, you'll see 3 significant, 4 and 4. Therefore, you round this off to 3. I'll do the scientific one. 1, keep the 0, keep the 9, use the 0 to round off, and that would be 1.09 times 10 to the 4th torr, which means I better go back and write my answer in. If you think about it, look out, warning, time for Dr. White's artwork. On a board, I'm not, in a classroom, I'm not that much better. If you have a piston right here and you reduce the volume by pushing it down, notice the pressure goes up. And that's how your hand pump works. Or if you go to a gas station to get air, that's how the compressor works. It compresses air to make a higher pressure. But I taught you that before. All right, let's continue. Oh, wrong thing. Everybody see the ideal gas law on there? Thank you. All right, I didn't do Charles' law and I will not do on the final. All right, but the ideal gas law, which is my favorite mathematical expression, one of them in chemistry, is PV equal nRT. And P is pressure, V is volume, N is moles, and hold on 1 second. Get rid of the little red squiggly line. And N is moles, R is the universal gas law constant, and T is temperature. Everybody, pay attention. Watch. Common mistakes students make. Pressure has to be in atmospheres. I've yet to see a gauge ever in my life that measures atmospheres. It's always torr or millimeters of mercury, or in some plants in the United States, inches of mercury too. But we won't deal with inches of mercury in my class. Therefore, I'll show you in a second, you have to convert the pressure from torr or millimeters of mercury to atmosphere. Volume is liters. I'll always give you that in liters. N is in moles. I have yet to see a balance that measures out moles. It measures out grams. And therefore, you're going to have to convert from grams to moles. Temperature is Kelvin. I have yet in my life to see a thermometer or temperature probe that measures in Kelvin. It's usually degrees C or Fahrenheit. In my class, I use degrees C, Celsius, so you'll have to convert to Kelvin, which I give you those. And finally, the universal gas law constant, which I will give you, is 0.0821 atmospheres, liters, moles, K. Now, the fun thing about the universal gas law constant here right here, the important thing is this tells you what units, in case you forget, these should be in. Atmospheres, pressure, liters, volume, moles, well, you can get from grams, and Kelvin, temperature. And therefore, that tells you what units the different things should be. Let's clean this up. Now, one of the things I taught you about PV equal nRT is when to check your tires, which was a problem on test 3. And I asked you what equation, how do you know using the equation when to check your tires in the winter or the summer? And in the winter, temperature goes down. These are constants, P, N, and R. Therefore, your pressure goes down. You better check your tires. In the summer, your temperature, your tires go up because it's hot outside. And therefore, if this is constant, this is constant, this is constant, the temperature goes up, the pressure must go up. And I told you back in 1995, when we had a brutal summer, the temperature here for over 2 weeks, daytime temperature, not the field temperature, real, was above 100. And even at night, it was quite hot. You saw a lot of cars on the expressway. Dr. White drove from where I live to by Great America because that's where I was working at the time at a company called Borden, no, Borden, no, it was PPG. No, it was PPG Mazer. And I could see cars pulled over in trucks with blowouts. And therefore PV equal NRT. Do I have time? I do. Time for a Dr. White story. I don't have too many more. This has nothing to do with on the test, but I just remembered when I worked at PPG Mazer, which was in Gurnee by Great America, I was given this one project to fix a way of testing a product for a certain parameter. And someone at the PPG main research center had developed it and was not that good of a test. It was based on a Navy test for a certain parameter called, let's see, it wasn't iodine value, a percent ethoxylation or EO value. And I got it to work better, but there were still some things I couldn't understand about it. Why? And I asked my boss, who I talked to, whoever developed it, because he had told me someone at the headquarters had. He said, yeah, call Dr. Dalmer. And throughout my life, as you know, Dr. White uses humor a lot, and it slipped out, and I said, whoa, is that Jeffrey's father? And my boss said, yes, and don't ask him about his son. And if you're not familiar, Jeffrey Dalmer was unfortunately the hideous person who in Milwaukee killed people and ate them. And later on, he was killed, unfortunately, or fortunately, I don't know which, in prison. But every time I talked to Dr. Dalmer, his father, in the back of my head, it was like, don't ask him about his son. And the other part of my head said, oh, go ahead, ask him. How'd you go wrong with your son? True story. Life is sometimes stranger than fiction. And every time I talked to him, that battle in my head, ask him about his son. No, don't. And I never did. He was a very nice man. I never met him face to face, but that's a true story. Once again, I'll call my famous, world famous thumbs up people. Do you see the practice problems? Thank you. I'm going to have to tweet out, I have the best thumbs up people this summer ever. Dr. White does tweet once in a while. All right, let's look at a PV equal NRT. Oh, let's have fun with a burp. When you burp, most of the gas, if not all of it, is carbon dioxide, CO2. So the question is, if you burp 86.75 grams of carbon dioxide, CO2 gas at 545 millimeters of mercury and 34.6 degrees C, then what is the volume of your burp? So what are you trying to find? Volume of your burp. What are you given? The weight of the burp. No, I won't burp for you. And what is the pressure? Notice it's 545 and it's in millimeters of mercury. What's the temperature? It's 34.6. And important information also under your name will be R is equal to 0.0821 atmospheres liters mole K. Now, let's take a look at this right here. This is essentially the problem. You're asked to find volume. You're given grams, you're given pressure, you're given temperature. Is anything changing? No. 15 points. What do you know? Well, nothing is changing. You're dealing with a gas. You're asked to find a property gas. Immediately, you should know PV equal NRT. What are we being asked to find? Volume. How do we find the volume? We need to get rid of pressure. We divide by pressure because anything divided by itself is the number one. And therefore, I look over here and say, I'll divide this side by pressure. Whatever you do to one side, you have to do to the other. And therefore, if I divide this, P divided by P is 1, 1 times V is V. On this side, nRT divided by P. Now, each of these has to be in the right units. And special announcement. Students make the following mistake, and they did on test 3, and that is they don't change pressure, temperature, and moles from grams to the right units. If you don't do that, guess what? You get it wrong. And Dr. White, well, in the old days, would take out his red pen and go, wrong. I don't do that now. I just don't give you the points. So make sure when you're doing a PV equal nRT problem, you use the right units. Look at R, that's your guide to tell you. And I give you that. Let's get back to the problem. All right, so to put it in the right units, pressure has to be, as you see here, in atmospheres. So how do you put pressure in atmospheres? Use your good buddy, your good friend. Yes, I'm going to do it. Unit analysis. What are you starting with? Millimeters of mercury. What are you going to? Atmospheres. Atmospheres goes on top of this magic ratio. It's not magic, it's unit analysis. Whatever you're trying to get rid of goes underneath the ratio. Where do you get these numbers? 1 atmosphere equals 760 millimeters of mercury. It's an important information. I used to make students memorize that. I don't now. Tea break. And now you have this number divided by this units. The units cancel out. You're going to be in atmospheres. 1, 760 are exact numbers. 3 significant, 3. Now, this is one of those problems you can round off at each step, which Dr. White likes to do, or you can wait till the end and round it off. And on the final, just like I did in the hourly exams, we have problems like that. I will calculate both ways, and both answers, if they're different, are correct. So we have this for pressure, three significant figures. Next is temperature. Temperature, look at PV equal nRT, K. Temperature in Kelvin is equal to degrees C plus 273. Remember, 273 is an exact number. And this will be given to, boy, I'm being too nice to you people. Anyways, degrees C plus 273, what do we have here? It's this. And remember, when you add, this is an exact number, 1 past the decimal, 1 past the decimal. You can keep a secret. On this one, people make mistakes. So if you don't do it, I don't take points off. That's the only time I ever do that. Shh, don't tell anybody. All right, so now we have pressure in atmospheres, temperature in Kelvin. What do we have left to do? Well, N. N is, look back here, moles, because we know this is atmospheres, pressure, liters volume, temperature, K. Well, what's moles? Well, I can get it from grams. How do we do that? 1 mole of a compound equals the molecular weight of a compound. Therefore, if we start with grams, we want to get the moles. Time to use your good buddy. Oh, I won't do it. Your good friend, unit analysis, what you're trying to get to goes on top of the ratio. What you're trying to get rid of, grams of CO2, goes here. And therefore, if you look, you have this number, 1 mole. What does it equal? The molecular weight of CO2. How do you find the molecular weight? It's the sum of all atomic weights. And in this case, you have one carbon. Remember, on the final, just like your hourly exams, I'll ask you, please use proper significant figures. And I'll also ask you, please use 3 significant figures for all atomic weights. And carbon is 12.0, 2 oxygen, 16.0. Do the math, add it up, get 44.0. Do the math, 4 significant, 3 exact number, 1, 3 significant figures. Now, I've taken the time to do this, and actually, I put in P first. No, I put in N, I did that right. N is here. R, the universal gas law constant. Temperature is this, and the pressure is this. Now, when you do multiplication or division, you get the same number of significant figures as the number that has the lowest significant figures, 3. Notice R is 3. This is a calculated number, not a defined number, is 3, 4, 3. Therefore, 3 significant figures. And your answer is 69.4 liters. That's one heck of a burp. And notice I have down there both ways, and that tells you if you round it off at the end or at each step, you get the same, which doesn't always happen, but in this case it did. All right, let's go back to the review, and we have Dalton's Law of partial pressures, and that is the total pressure, P total, tea break, the total pressure of a mixture of gases is the sum of the partial pressures. And notice here, P1 is the partial pressure of a gas. What's the partial pressure of a gas? That's the pressure of each component of a mixture if it were alone. And therefore, total pressure equals partial pressure. And I did a problem like that. You can go ahead and look at that on test 3 on your own. Now, the important thing I covered either here or in solutions, but I'll talk about it now, and that's boiling. And when you boil, warning, more artwork from Dr. White. If you have a beaker with water in it on a hot plate, that looked pretty good hot plate. There's the cord right here. But anyways, eventually you'll see bubbles form in here, and they'll go to the surface. And those bubbles are water vapor, water in a gas form, in a temperature which they normally would be a liquid. And you see enough bubbles coming, and they come to the surface and collapse. And when they collapse, they let off water vapor. Water is a gas. Therefore, you have a gas which has a pressure. Out here, you have the air which has the pressure, and the boiling point of the liquid is the vapor pressure of the liquid from the bubbles equals the atmospheric pressure. Sometimes that's called this boiling temperature, but the boiling point. Now, because the atmospheric pressure affects the boiling point of a liquid, the higher you go on the earth, the lower the atmospheric pressure. Therefore, you need less energy here to make the vapor pressure equal atmospheric pressure. Therefore, higher altitude, the lower the boiling point. So when you go higher altitude, this abbreviation for boiling point temperature, the boiling point goes down. Now, the opposite of that is how pressure cookers work. In a pressure cooker, what happens is I should have also put here. When you go up at a higher altitude, the air pressure goes down, atmospheric to boiling point. Now, in a pressure cooker, which Dr. White doesn't like to use, because I worked in a high pressure gas reactions, and it's quite dangerous. When in a pressure cooker, you can find the water that's boiling, the atmosphere pressure just inside the cooker goes up. Therefore, the boiling point of any liquid in there goes up. Higher temperature means you cook your food faster. And this also explains evaporation, how when a liquid becomes a gas, it takes energy. And that's why in hot weather, men sweat, but women perspire. Seems politically correct. All right, next I talked about solutions. And what is a solution? I won't ask on a test, but a solution is a mixture of different chemicals or compounds which neither, hold on, it's the wrong number. 2 more times. 1 more time. Stop. Now stop. Thank you. Didn't want to listen to me. Let's get back to solutions. And solution has 2 or more components mixed together, which none of the components change their chemical identity. In other words, they don't react. And when you make a solution, it's homogeneous. That means it's the same throughout. And can everybody see the solution around me? Air. And air is a solution. It's a mixture of oxygen and nitrogen. If I'm here and I can breathe, if I go over here, oh, I can't breathe, there's no oxygen. No, it's the same, it's homogeneous. It's time for awful Wednesday humor. And I get to, how should I say, inflict my awful humor on you. And they pay me for this too. Anyway, solutions. Ooh, here's a solution. My tea. It's got sugar and the component, water, and the components from the tea, which Dr. White knows. And if you take my organic chemistry, I'll teach you about what are different things in the tea. And coffee too. Now, when we talk about a solution, you should know there are 2 important terms. One is solvent. Come on, red pen. Solvent. And solvent is the component of the solution present in the greatest amount. The other components, you can have 1 or more, only 1 solvent, but you can have many solutes. And the solutes are all the other components. So if you had 125 grams of water and 350 grams of ethanol, which one is the solvent, which one is the solute? I'm going to steal some tea while you think. And let me check something. See, somebody already beat me to the answer, which is a good thing. All right, let's do this. This is present in the greatest amount, so ethanol is the solvent. and water in this case is the solute. Most times in our life, water is a solvent, but Dr. White likes to be tricky. And if I look at the clock, I see we're just about ready for our break. So instead of talking the next thing, let's take a break, come back at 9:55. That's when the big hand is on the 11 if you have an analog watch, or you see 9:55. I'll see you in 5. I'm going to go stretch. All right, ring, 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 ring. I'm back. Hopefully you are too. All right, let's get back to work. Thumbs up, people. Can you see solutions? Thank you. All right. Now, important thing is a colloidal dispersion. And a colloidal dispersion is not a solution. At first glance, you say, oh, it's a homogeneous mixture, but it's not a solution. How do you know that? Because in a colloidal dispersion, that's where small particles of one substance is dispersed, not dissolved in a amount of another substance. Particles are suspended, not dissolved, in a liquid or whatever. You can have gases too, I think. I don't know. But it's not a solution. Why? Because those suspended particles scatter light. Ooh, it's time for one last time. Dr. Whitelow's flashlights. Is this a solution or a colloidal dispersion? Oh, light goes through, red light. And therefore, you know this is a solution. If I had milk, and no, I'm not going to run downstairs and get a glass of milk, but if I did and I did this, you wouldn't see any light come through it. And the same thing if you did that with ketchup, mayonnaise, latex paint, also your blood. Don't try that ever at home. And you'll find those are colloidal dispersions. When I ask, give an example of a solution of colloidal dispersion on a test, and the answer is yes, and I did. And examples, like I just said, of colloidal dispersions would be milk, blood, latex paint, also mustard, ketchup, and there are other things too. Mayonnaise is another colloidal dispersion. Now, one of the most important things I will teach you this semester is the rule of thumb. Rule of thumb means it's true about 98% of the time. A law is always true. A rule of thumb, most of the time it's true. Now, and that is like dissolves like. And that is like are soluble in like solvents. And what that means is polar solutes are soluble in polar solvents, and nonpolar solutes are soluble in nonpolar solvents. Example of things that are polar: water, alcohol, salts like sodium chloride are polar. What are nonpolar? Vegetable oil, gasoline, Vaseline, baby oil, grease, and dirt are nonpolar. And because grease and dirt are nonpolar, that's why water won't get it off. You need soap, and I'll teach you about soap if you take my organic chemistry class ever. And how soap works uses like dissolves like. And I gave you a problem. I suggest you go back and look at test number 3, where I said a certain compound is soluble in water, but not vegetable oil. And another compound is not soluble in water, but is in vegetable oil, which identify the polarity of each substance and explain why. And a lot of you had problem with that. And because something's soluble in water, it's polar, and that one was polar. If it's not soluble in something like vegetable oil, that tells you it's also polar. The other one was soluble in vegetable oil, which tells you it's nonpolar. And go back and study that. Now, there's certain definitions you should know. One of them is the solubility of a solute, and that's the maximum amount of solute that will dissolve in a given amount of solvent. And then other definitions you should know are a saturated solution is a solution that contains the maximum amount of solution that can be dissolved under conditions that solution exists, such as temperature or pressure. And really what you mean is you've reached the solubility limit of that solute when you have a saturated solution. Now, the opposite of saturated solution is a dilute solution. And that's where you have a small amount of solute relative to what you could dissolve in there. And another similar to saturated, but a little less, is concentrated solution. And that's where a solution that contains a large amount of solution relative to the amount you could dissolve. And that's why if you go to the supermarket, you can still buy, even though most people buy already made in a bottle or a plastic jug, orange juice, you can still buy the concentrate they call it, where they take out a lot of the water from the orange juice and you're left with a lot of the pulp and other chemicals. They are chemicals, but you think of them as food that are in orange juice. Now, one, excuse me, important definitions, aqueous solution. Aqueous solution tells you it's a solution in which the solvent is water. Aqueous, water is the solvent. And it's abbreviated by bracket, the letters AQ, close bracket. Whenever you see that anywhere in chemistry, you know the solvent is water. Now, we talked about concentration. Concentration is how much of a solute is present in a solution. Again, concentration, how much of a solute is present in solution. Now, there are different ones. Two that I will not ask you on the final are concentration by weight, and that's where you have percent weight divided by percent weight of the solution. You generally, if you buy stuff, you'll see percent of an active ingredient. The higher that is, the better it is for you to buy. Oop, hold on. Percent weight of tea in here is high. So is sugar. I like sweet tea. But anyways, that won't be on the test. Another concentration is percent volume, and that's volume of the solute per volume of solution. That won't be on the final. But if you go and look at a bottle of wine, you'll see on the label percent alcohol, say good wine, 8 or 10, 15%. Oh, by the way, Dr. White loves white German wines because I was in Germany a lot. And my favorite is Pierce Porter Golden Trocken, either their Cabernet, Spätlese, Auslese. In German wines, Spätlese means they wait a while to pick the grapes. Auslese means they wait a long time. What happens is by waiting a long time and when it gets cold, you lose water from the grapes and they become sweeter. So Cabernet is, in German white wines, is sweet. Spätlese is sweeter, and Auslese is very sweet. My sister doesn't like sweet wines. I do. By the way, Dr. White doesn't like French wines. German wines are better. Now, the most important thing I taught you about concentration is molarity. And molarity of a solution is a ratio giving the number of moles per liters of solution. Now, molarity, which is shown by capital M, is moles per liter, but 1 liter equals 1,000 milliliters. So this is a better one to know. And on test number 3, I asked something like, And I'll let you try this. What does this mean? And what is the solvent? And don't tell anybody else in chat. Let everybody have time to finish it themselves. All right, time's up. And the question is, what does this mean? If we look here, capital M, molarity, moles of solute per 1,000 milliliters. So what this tells me is 8.13 moles, and now you know this is hydrochloric acid, per 1,000 milliliters. That's what this means. What is the solvent? This tells you the solvent is water. And notice I have very important, know this. And when I say know this, in the past, I'd say you'd have to memorize this. No, this I think will be given to you in important information. Now, when we talk about molarity, and let's go to the practice problems. A couple of things, give an example of a colloidal dispersion. I've done that. Give an example of a solution. We talked about that. Name the solution. What's solvent and solute? We did that. What does this mean? Well, we just did that. What's the solvent? Now, let's look at number 8. How many moles of sodium chloride are in 125 milliliters of a 3.45 molar NaCl solution? And what do? You figure out, what am I being asked to find? Moles of sodium chloride. What am I given? 125 milliliters solution. I should ask, but I didn't, but nobody's yelling at me. Everybody see the problem set? Oh, you should have yelled at me. Actually, I should have yelled at myself. Let's try again. I clicked on it to show. All right, now does everybody see it? Ooh, I even got a double thumbs up. I'm doing good. Let's go back. I talked about what are examples of colloidal dispersions. I talked about give an example of a solution in your daily life. Here I have examples which you should practice. What's the solvent? What's the solute? Remember, solvent is present in the greatest amount, solute, the other components. Talked about what does capital M mean? Molarity, moles per 1,000 milliliters. What does the AQ mean? Solvent is water. Now, let's do number 8. How many moles of NaCl are in 125 milliliters of a 3.45 capital M sodium chloride solution? And now, what are we being asked to find? Moles of sodium chloride. What are we given? 125 milliliters of the solution and 3.545 capital M NaCl. Ooh, what does that mean? It means molarity. And molarity, as you see, I wrote down, you should know, in this case is 3.45 moles of sodium chloride per 1,000 milliliters. And now if I look at this, I say I'm trying to get, I have this number right here. That's all I'm really given. I'm trying to get the moles. I'll put whatever I'm trying to get to on top. Whatever I'm trying to get rid of, I'll get on bottom, because I'm using my good friend, my good buddy, unit analysis. And where do you get these numbers? From here. 3.45 moles of sodium chloride per 1,000 milliliters. Milliliters cancel out. I'm left with moles. Remember, when you're doing a multiplication division, the number of significant figures in your answer is the same as the number of significant figures that's lowest than the numbers you're multiplying or dividing. This is 3. This is 3. 1,000 is part of the definition. Therefore, this is an exact number. And therefore, it plays no role in the calculation of significant figures. This is 3, 3. Our answer is 3. Thumbs up, people. Can you see the whiteboard with the pressure on there? The whiteboard is not white because I've been writing on it. Ooh, profound. Ah, come on. There. All right. How many moles of HBr are in 351 milliliters of a 4.69 capital M HBr solution? Your turn. I'm going to share the fun. And when you're done, look up and give a thumbs up or a smile. I see someone out there has a monster coffee cup. Oh, and a pretty picture on the front. All right, everybody done? All you thumbs up people who don't have their video on, I assume you're done. There's nobody screaming at me. You should never scream at the instructor, but you can. It's allowed. All right, let's do it. What are we being asked to find? How many moles HBr? What are we given? How many milliliters of solution? We're also given this number. And as soon as you see capital M, you know that's molarity. And what does this mean? 4.69 moles HBr per 1,000 milliliters. I only have one number to start with, really. This. I had some ratio. I multiplied by what units do I want my answer to be in? My cursor was causing everything, moles of HBr. And now we'll use our good friend, our good buddy. Hold on, I got to do it. Unit analysis, get my red marker out too. Whatever we're trying to get rid of, our go-to goes on top. Whatever we're trying to get rid of units goes underneath. Where do I get those numbers? From here. Don't forget, here would be moles, HBr. Now I have a bad hair day. Dr. White is having a bad tablet day. You have moles of HBr. What do we have down here? Milliliters. Where do we get these numbers? From the molarity, which is moles, 4.69 moles of HBr divided by 1,000. And now, before I pick up, I notice milliliters divided by milliliters, pick up my calculator, that is, cancel out. I'm left with the right units. So I set that up correctly. That's how also unit analysis is your good buddy and your good friend. And I'll now go to my calculator. Hit the button and I get this. If you notice, 1,000 is the exact number. How do I round that off to 3? I'll let you try first. Time's up. Keep the 1, keep the 6, keep the 4. Use this number 6 to round off. Is it 5 or higher? Yes. I'll drop that and everything else, increase the 4 to 5. So it's 1.65 moles of HBr. And that's your answer. Now, it's important to know this step. Why? Because the next problem I'm going to talk about our concept, and that is molarity two-step problem. And this is a step where you're trying to find out how many grams of a solute are needed to make a certain amount of molar solutions. And by the way, as I have in test 2 and test 3 and the final, I have these in important information, which we've already used. I'll call my wonderful thumbs up people. Can you see the problem set? Thank you, wonderful thumbs up people. All right, let's look at number 11, 10 points. This was on test 3. A lot of you had problems with it, so I'm going to take my time. How many grams of sodium chloride are needed to make 345 milliliters of a 6.789 capital M NaCl solution? Well, what are we given? We're given, or what are we trying to find? Grams of sodium chloride. We're given this, milliliters, and we're given molarity. And there's no way I can go from this to this. No way. If you find a way, let me know. We'll be rich beyond my wildest dreams. No, you can't. So you need 2 steps. And I will give you that. As you can see, let me bounce back. Hang on so you don't get dizzy. The molarity 2-step problem, step 1, milliliters to moles. Step 2, moles to grams. Therefore, in step one, I'll ask once again, everybody see the two-step problem? Thank you. Uh-oh, I think I'm seeing thumb fatigue. People's thumbs are, oh, I think I can do it. All right, step one. We go from milliliters to moles. How do we do that? Here are the milliliters. We want to go to moles. We use unit analysis, our good buddy, our good friend. Whatever we're trying to get to goes on top. Whatever we're trying to get rid of goes underneath. And where do we get this number? From the molarity. Capital M means moles per 1,000 milliliters. In this case, 6.789 moles of sodium chloride per 1,000 milliliters. And here we put the numbers in. Here I have milliliters, 3 significant figures. I have moles of sodium chloride, 4,000 is the exact number. When you're multiplying and divided, the number you get in your answer should have the same significant figures as the number that you're multiplying or dividing that has the fewest, and therefore 3, 4, exact number, 3. Now, this is one of those problems where there are multiple steps. If you want to wait till the end to round off, you can. Dr. White is at each step round off, and that's why I rounded off to 3 significant figures. Now, is that what we want? No, we're trying to get the grams of sodium chloride. So the second step is moles to grams. Here I have my moles of sodium chloride. I'm trying to get the grams. What's the ratio I use? I use my good buddy, my good friend, unit analysis. I think I'm getting siren fatigue too. I didn't use it, but I'll do it tomorrow at least once. Grams go on top, sodium chloride. Moles go underneath. Where do we get this? Important information, 1 mole compound equals the molecular weight in grams of the compound. And the molecular weight equals sum of all atomic weights. Therefore, sodium chloride, the 3 significant figures, sodium is 23.0, chlorine, which a lot of students get wrong, but it's 35.5 added up. Here's the molecular weight of sodium chloride. For every 1 mole, there's so many grams, 58.5. 3 significant, 3, 1 is an exact number, 3 significant figures. And one of the things why this is important is when you go to make a stock solutions, which we do in both the chemistry labs and chemical plants, we have a way of making up certain concentrations by using what I just showed you. And that's the review for test 3. Tomorrow I'll do test 4. If I look at the clock, I've got a few extra minutes. So it's time for Dr. White to give you some useful advice in life. And it's free, but it's useful advice. All right, when I started working in the chemical industry, I was very lucky. I was adopted, so to speak. Actually, I had he was my mentor at one company, and that was Sidney Shapiro. When I started at that company, it was the first industrial job I ever had in terms of the chemical industry. In the summers, I worked in places to make money, like loading docks, supermarkets, and all that to get me through college. Sid was a chemical engineer who was also really a sharp chemist, but his degree was in chemical engineering. And when I joined the company, I was like in my about 28, I think, or 27. Sid was near the end of his career. He was already in his 70s. Sid had started with other people, a whole industry, making chemicals from fats and oils. And I actually carpooled for a whole year with Sid. And that's when there was the gas price went real high and we carpooled. And for every day, it was 45 minutes to work, 45 minutes home. I got an education in real life, and he would quiz me on things. I had a problem today. Is how would you solve it? And I learned things from him. And one of the most important things Sid taught me was common sense is not common. And I'll say that again. One of the most important things Sid taught me was common sense is not common. And throughout my life, I have found that to be true. And it also helps when you're solving problems. Now, there was one problem at one company I was asked to solve, and I might have told you this, but I'll tell you it again because I got a couple minutes to kill. But anyways, I was at Borden Chemical, and I was a senior R&D manager, and part of my job after a while, when I proved to everybody there I could solve problems nobody else could, the vice president of research and development, who was my boss's boss, I reported to the assistant vice president, called me into his office, and his name was Dr. Calvin. What's Cal's last name? I can't think of it. Cal, everybody called him. Called me and said, we got a problem with this area. And it was in the coatings area. And I told Cal, I don't know anything about coatings. I've never worked in that area. He said, yeah, I know that, but go solve the problem because we haven't. So I went to my boss, who that was part of his responsibility, and Cal had already told him to have Dr. White, me, solve the problem. And he had been trying with a whole research group that's separate of my research group that report to him in coatings to solve that problem. And the problem was, to save money, the company was closing a plant in Milwaukee and transferring all those products that were made in a plant in Milwaukee to a plant in Toledo, Ohio. And they could make it correctly in Toledo, Ohio, in Milwaukee, where they'd been making it for 15, 20 years, they couldn't make it correctly in Toledo. And this was an important product because it was bought by one of our biggest customers, General Motors. And General Motors said, until you can make it right at the other plant, we're not going to let you close that other plant. So to keep one whole plant open for one product, it was costing the company about $100,000 a month. That's a lot of money to blow because you can't solve a problem. Well, they had already worked 6 months on it. That's over $500,000, 600,000 for those of you keeping count. And the CEO was getting upset. Why are we losing all this money? You solve it. It shouldn't be that hard to solve. And he also knew about me, and the VP, Cal, said, have Dr. White solve it. So common sense. You're making it one plant, you can't make it in the other. Something's different. That's common sense. So what did Dr. White do? I went to the plant that could make it right, and I went and watched it, and I also videotaped them making the product. Then I went to Toledo and went to the plant and watched them making the product. And guess what? They didn't do the same thing, which common sense is, if you do the same thing, you'll get the same results. Well, they weren't. And I didn't ask my boss, couldn't you figure that out? How dumb are you? I was going to use the word I shouldn't use, but how stupid could you be? I was thinking that. And one of the problems why I thought about it was there was a specification for pH, and you know about acidity, and the pH at the company that couldn't make it was too high. And what was the problem? Besides watching them, I took an inventory and watched what actual chemicals they use. In the company in Milwaukee, they used a 28% hydrochloric acid. At the company in Toledo, they had only in their plant 32%, which was more concentrated. Did they change the amounts in the procedure in Toledo? No, which meant they were using way too much acid, which is why the pH was out of spec. So first of all, whoever wrote the original procedure didn't do a good job, and I had to clear that up too, but it wasn't that hard. But what it came down to was using common sense. You can make it here, okay? You can't make it here. I'm out of focus. Now I'm back in focus. There's something different. Look for what's different. It took me a whole week, actually less than a week, to solve it like that. Now, my boss was quite mad at me. Why? Because I made him look like a fool. I didn't plan on it, but when they saw how I solved it, my boss's boss went to him and wasn't too happy with him. Why didn't you do that? It wasn't that hard. And it wasn't. If you always remember the lesson Sid Shapiro taught me, that is, common sense is not common. You expect people to use common sense, they don't. With that, I went the whole minute over. I'm sorry. With that, I'm going to say goodbye, gang gesund, be healthy. I'll see you tomorrow. I'm going to do some more review, and bye. Bye. Stay healthy. And if anybody has any questions, I'll stick around.